Hey class, welcome back. I'm just gonna go over these two problems from the last section of 2.6 as I promised. In example 4, we are referring to a problem on the book known or describes an airplane flying over a radar, and they give us a picture here that would be the ones to make reference, so there is a little more information than just what the problem is saying. And so let's just go over the problem here real quick. The airplane is flying on a flight path that will take it directly over a radar tracking station. That means that it hasn't got there, right? So it's moving towards the radar. The distance s is decreasing at a rate of 400 miles per hour when s is 10 miles away. What is the speed of the plane? So in this example, they actually give us the picture, and the picture is of the radar here. They give us that this distance is 6 miles away. They give us that this is the s value, the s distance, and that means that the distance from the airplane to the radar. And then they're saying that the distance from the airplane to be perpendicular to the radar will be x. So this is the distance for the airplane to actually go over the radar, and this is your s. Now they give us that picture and they're making reference to that picture, so it's not like we're guessing that that's how it looks like. So it was given. So going back again, they give us the distance s is decreasing, right? That means that as you get closer, the airplane gets closer, then the distance of s gets smaller. So it is decreasing, and is decreasing at this rate, so 400 miles per hour. So the rate of change of s is 400 miles per hour. So because it is decreasing, actually we would actually interpret that as being a negative rate. That's what it means to be decreasing. That means that the distance is getting smaller. And so because it is a rate, we want to translate this mathematically. And that is going to be a rate that will be a ds. The rate of s over time is going to equal negative 400 miles per hour. And again, it's negative because the distance is decreasing. If you're flying away from the radar, then that would be there's a positive increase. There's an increase of distance, so therefore that would be a positive rate. And this happens when s is 10 miles away. So that means when this is 10 miles away, that's the speed for which this is changing. The question is asking us, what is the speed of the plane? We measure the speed of the plane by the way that it changes over this path. So we're actually looking for the speed of the plane, which means is the rate of change of this distance, which in this case is described with x. So what we're looking for is dx dt. We're looking for the rate of change of x over time, or when s equals 10. So we're given this and we're looking for this. So we gotta find an equation that relates s and x. Well, we can see that this belongs to a Pythagorean triangle. Sorry, right triangle, and we already have this side. We already know this side. We already know this side. We can figure out this side, right? So then, therefore, we can use the Pythagorean theorem to connect all these sides. So x squared plus 6 squared equals s squared. Then we have if we found the equation, which is sometimes the hardest part. In this case, it was pretty straightforward. But then since we want to work with the rate of change, we're gonna take the derivative on both sides of the equation, and that will be implicitly, right? So we'll take the left side and we'll take the derivative of the right side in respect to time. So when you do so remember that x is changing over time. So the distance of x depends on time. Because x depends on time, that means x is a function of time. So therefore, when you take the derivative of x, you have to treat x as a function. So as its own function that we don't know how it looks like, right? But it's a function. So when you do the derivative of this, you're going to have to use chain rule. So bring down the 2 in front, leave the inside as it is, subtract 1, and multiply by the derivative of the inside, which in this case is dx dt. This is a constant, so the derivative of a constant is 0. The derivative of s squared, well, s is also a distance that changes over time. So that means it's going to be a function of time. So therefore, you have a function inside a function. So you apply the general power rule. So bring down the 2, multiply by the inside function, subtract 1, and then multiply by the derivative of the inside. And there you go, right? So now we have, if you notice, we have everything that we need. We know, well, actually, let's see, we have everything we need, right? We know we're looking for this. We know what S is, that's 10 miles, and we know what ds dt is. What we don't know is X. So how we're gonna find X? Well, you know that there is, in that moment when you have 10 miles, that this can give you enough information to find the appropriate value of X. Whenever this is 10 miles, can we find what X is? And that's just, again, simply an equation of Pythagorean theorem. 6 squared plus x squared equals 10 squared. Solve for X, and that gives us X equals 8. Now we could have positive 8 or negative 8. Now because you're going towards this, the distance is becoming from greater to smaller, meaning as you get closer, the distance will be 0. That means that you're in a positive value here. So the distance here is 8, right? If you would have been over here, then you could argue that that's a negative distance, right? Now, by the way, so this is a positive distance, but we're going to argue that this is actually going to give you a negative velocity, right? You're going, the distance is decreasing, so that will be a negative. So we'll see that in a second. Now we don't have to make that argument. We're just the math is gonna work out that way also. So we know that X is 8, so we're gonna replace that in there. So we did that. We're gonna multiply this by dx dt. We're gonna multiply this by 2, multiply by S, and multiply by dx dt. And then now we have everything we need to be able to solve for dx dt by using simple algebraic division of both sides of 16. This will cancel. Everything is going to come out to be negative 500, and that's great. This is good. This actually makes sense because we are going in. Their distance is decreasing. That means your derivative should be negative, right? So you're decreasing, your derivative should be negative. Now this is the velocity, but they didn't ask us for the velocity. They ask us for the speed. And speed, as I mentioned before, speed is always positive. So what we're going to do is we're going to take the absolute value of the velocity, and that will give us the speed. So velocity could be negative because velocity has a direction. Speed is the magnitude of this velocity. So you're looking for, like, how strong is this? What is the actual rate of change of this velocity without the reference of the direction? So that's what the speed is the magnitude of the velocity, which means is the absolute value of the velocity. Always, always, always. No exceptions. So the next example, we're going to talk about an engine that is referred to a figure of 2.38. So this is your figure right here, right there, and right there. Now it's important for us to sort of get familiar with the type of problems that we have, but we don't have to become an expert of you don't have to be a mechanic to be able to figure be able to answer this question that we're going to have here. So we have a 7-inch connecting rod, which is fastened to a crank of radius 3 inches. The crank shaft rotates counterclockwise at a constant rate of 200 revolutions per minute. Find the velocity of the the piston when the angle is pi over 3. So I try my best here to make the picture of what's going on. So let me describe what happens here. So this is the piston. Now this is moving left to right. So this box is moving left to right, and there's like a something that makes an explosion to be able to spark that makes this explosion to move this in that motion. So this is the rod right here, and there is this crank right here of radius 3. So what happens here is that this is fixed, and then what happens is that this is also fixed, and this is fixed. So what happens is that if this is move to the front, what's going to do is this rod is going to be pushed to the front, and then it's going to make a full rotation, and then it's going to come back over here, and it's going to start over again. So this keeps moving like this, so this is fixed, so it's going to be moving, helping it rotate around this ship. So as this is moving, so the question is, if we translate this problem over here, this is fixed and this is fixed, what's actually changing in this problem is the distance from here to here, because this actually gets closer, right? As this gets closer, then this distance gets shorter. As this gets further away, then this distance gets greater. So this is actually moving, right? So this is moving, and they're asking us to find the velocity of this part right here, of the what they call it here, the piston, right? Because this will determine the velocity of the piston whenever you have an angle that is pi over 3. So whenever this is just pi over 3. At this moment, what is the speed of this piston? So we can find the velocity of this piston by recognizing how fast is this distance changing. So that the translation is, can we find the rate of change of x whenever the angle is pi over 3? All right, so that's the question. And we can see here that they're giving us a relationship between, they're giving us something about rotation, right? They're giving us that the rate for which the rod is rotating is at a rate of 200 revolutions per minute. So that means that this piston right here makes 200 revolutions in one minute, and so that's sort of giving us something about the angle, right? This is telling us something about the specific angle. So we can see how this rotates, how fast this is rotating, by using the information that they give us here, and that's what we're going to find out first. So what does it mean about the angle? How fast is the angle changing? It's actually determined by what they give us up there. They're saying that the angle changes over time by this rate. It's saying that it takes 200 revolutions per minute. Well, how do we rotate? What does it mean to be a revolution? A revolution means it makes a full rotation. That's one revolution. So it makes a full rotation, meaning that the angle to be in a full rotation, the angle has to be 2 pi. So one rotation is 2 pi. So you have 200 rotations, so you have 200 times 2 pi per minute. And that tells you how fast is the angle moving. So we already found how fast is the angle changing, right? And this is consistent, right? This is consistent. So that's always changing the same rate. But we're going to use that to be able to find how fast is the length of the piston, or the piston is moving a long time when the degree is pi over 3. Now, if we look at this and now we try to make sense of it, we already know what this is. So can we find a relationship between this angle and this length? Well, we cannot assume that this is a right triangle. In fact, what we're going to use here, instead of using the fact that we know this is a right triangle. In fact, it won't be a right triangle. But instead, what we're going to use is, well, what other options do we have? Well, we also have the law of cosines. And the law of cosines says that we can find a relation between the sides and a specific angle. So that's going to fit perfectly. Now remember, if you already know an angle and you know the sides, then you want to use this in the right order. So if you have the angle, which is going to be theta, and you have the opposite side, then that's going to be your a squared, and then here is going to be b squared, c squared. Those are going to be the other sides, and then you have negative 2 times the two sides. So these two have to be opposite of each other, right? This side is little a, this angle is big A, uppercase A. So now that you have that, then use that information to set up the cosine equation. So we have opposite side is 7 squared, one of the sides is x squared, the other side is 3 squared, and then we have x and then 3, and then you just simplify, and that gives us this equation. So we already found the equation, so there you go, we found the equation that relates x and theta. But now our goal is to be able to relate them to these two, right? So what we're gonna do, we're gonna take the derivative of both of them. Now remember that data depends on time, right? So it changes over time. So when you do that derivative of cosine, you're gonna treat theta as a function of time. Obviously x is also changes over time, so that's a function of time, so it depends on time. So when you do the derivative on both sides of the equation, the derivative 49 will be 0. When you do the derivative of this will be 2x times the derivative of the inside, right? Plus 0 minus 6 times the derivative of this. Because this is a function, we're going to use the product rule. I decided to leave the 6 outside and just take care of the product of this product rule, and then I'll deal with the 6 at the end. So I have to put a bracket here telling the reader that I'm going to first take the derivative of this and then I'll multiply by 6. That's just a choice that I use here. It wouldn't be a big deal if I chose to have this to be one of the functions and this to be the other function, right? It wouldn't be a big deal. It would give us the same result. Anyway, so derivative of this will be derivative of the first one, leave the second one as it is, plus, that's supposed to be a plus. Sorry, that's a plus right here. Plus x sine, the plus x, oh no, sorry. I know why I put a negative there. Okay, put a negative there because the derivative, so we're going to leave the x as it is, and we're going to multiply by the derivative of the cosine. The derivative of the cosine is negative sign, so that's why I already adjusted to the negative there. It would have been plus, but because of the minus sign, then that becomes negative. Then multiply by the derivative of the inside, which is d theta dt. So I use chain rule for this one, right? Derivative of the outside is negative sign. The derivative of the inside, leave the inside as it is, and multiply by the derivative of the inside. All right, then we're gonna go ahead and try to see if we can. We have everything we need, right? So we know what. Do we know what x is in this problem? We don't, right? It doesn't seem like we do, like we know what x is going to be. We know what we're looking for, dx dt. So we need to figure out how we're gonna find 8, right? We know what theta is, and we know what theta dt is. So let's figure out how can we find x equals 8, and that would be by looking at this equation here. So we take this equation before you take the derivative of it, and you do that on the side as a side work. So what was it? 49 equals x squared plus 9 minus 6x cosine theta, and you replace this with pi over 3, then the unknown will be just x. So you have 49 equals to x squared plus 9 minus 6x cosine theta, which is pi over 3. This is 1/2, and then we can subtract 9 on both sides. That gives us 40 equals to x squared minus 6x times 1/2. That gives you 3. So you have, and then we're going to subtract 40 on both sides. And then we have 0 equals x squared minus 3x minus 40. And then we can try to factor this out. So this will be x equals 40, that will be 5 and 8. And so this will also imply that x equals 5, x plus 5 equals 0 and x minus 8 equals 0. This gives you x minus 5 and this gives you x equals 8. You cannot have a distance that is negative, so here we're going to have x equals 8. So that's where the 8 came from, and so we're going to use that here. So see below. So plug in the 8, plug in your theta, plug in your 8, plug in your theta, plug in d theta dt, and simplify, right? 2 times 8 is 16, minus 6 here. This becomes 1/2. Then we have this sine of pi over 3 is the square root of 3 over 2, which we're going to be able to simplify with that 400 that we have here, so it becomes 200 pi. And then after this is just pure algebra. We're going to try to simplify as much as we can and then isolate the dx dt. So we see that these two, we distribute this -6, and that's how we got -6 over 2 dx dt. Plus, because negative times negative becomes positive, 6 times 8 times the square root of 3 times 200 pi will give us about 9600 square root of 3 pi. Factor the dx dt. Actually, we can actually simplify these two by using common denominator. So this becomes negative 32 minus 6 is negative, no, so that's 32. 32, let's do this inside. 32 over 2 minus 6 over 2 will give us 26 over 2, which is 13, right? So that's how we got the 13 there. We subtracted this on both sides of the equation. That's how we got that, and then divide both sides by 13. We put this in the calculator, and that's how we got negative 4018 inches per minute. So it is a rate, so that's why we have to put the units of measurement as a division, inches per minute. And we knew that from the beginning when they gave us the units of measurement of inches. Everything was in inches. Now it is negative because it is in this moment when you have pi over 3, the piston is still going in this direction. Is going that direction. So that's a negative direction, right? Well, actually, it's because the distance of x is actually getting smaller, right? So because the piston is getting closer to this little circle, then the distance is getting smaller, so therefore the distance is decreasing, so therefore the rate of change is negative. And there you go. I hope this is helpful. Let me know if you have any questions. I'll see you guys in class.